In this lecture, we're going to continue to build our encyclopedia of derivatives for the important functions that are used in pure and applied mathematics. Our attention now will be focused on the trig functions. First of all, recall that in an earlier lecture we established a difficult limit that we're going to now find indispensable, that the limit as h goes to 0 of sine h divided by h is 1. Now we tackle the computation of the derivative of the function sine x. First, as always, we form the difference quotient using a point x sine x on the graph and a nearby point x plus h sine of x plus h. So we form that difference quotient and we use the addition formula for the sine function to expand sine of x plus h. Now we take the limit as h goes to 0 of that difference quotient, and it breaks down into a sum of two limits, one involving a factor of sine x, which factors out, and a factor of cos x, which factors out. As usual, working with trigonometric functions involves some extra work. The second limit, sine h over h as h goes to 0, we have already established. It is 1. So now we know that the derivative of sine x is sine x times a limit we have yet to calculate. The limit as h goes to 0 of cos h minus 1 divided by h, plus cos x. Now to that limit. Multiply the numerator and denominator by cos h plus 1 to get the limit as cos squared minus 1 divided by h cos h plus 1. The important thing is that the numerator becomes minus the sine squared of h from our fundamental identity that sine squared plus cos squared is 1. The denominator will leave unchanged. Now with this latest limit, separate the expression into a product of three limits. There's a minus sign that factors out. Then you've got the limit as h goes to 0 of sine h divided by h. Then you've got that multiplied by the limit as h goes to 0 of sine h. And last of all, you've got the limit as h goes to 0 of 1 divided by cos h plus 1. Each of these limits we know. Sine h over h goes to 1. Sine h goes to 0 because the sine function is continuous at 0. And the limit of 1 over cos h plus 1 goes to a half. And the product of these three numbers is, of course, 0. So we have our first trigonometric derivative. The derivative of sine x is cos x. As an example, we can now find the equation of the tangent line to the graph of the function f of x equals sine x at any point on that graph. For example, let's choose the point pi over 3 sine of pi over 3. And the sine of pi over 3, you remember, is one of the things we know exactly. It's root 3 over 2. So we're talking about the point pi over 3 root 3 over 2. You can then calculate immediately that the derivative of sine x at that point is the cosine of pi over 3, which is a half. So the equation of the tangent line at this point is immediate. Y minus root 3 over 2 divided by x minus pi over 3 equals the slope, 1/2. Now let's turn to the cosine function. First we form the difference quotient. And again, we use the addition formula for cosine this time, and we collect terms in cos x and sine x in the numerator. Now take the limit as h goes to 0 and use your limit rules to write it as a sum of two limits. The first limit is the cosine of x times the lim as h goes to 0 of cos h minus 1 divided by h. The second limit is minus the sine of x times the limit as h goes to 0 of sine h over h. And when you work that out, the whole thing collapses to minus sine x. So the derivative of cos x is minus the sine of x. Now we can differentiate all of the remaining trig functions since they are all defined in terms of the sine and cosine. For example, the derivative of tangent is the derivative of sine over cosine. So that's the usual quotient rule. Denominator is cos squared, and the numerator is cos derivative of sine minus sine derivative of cos. And when you work that all out, in the numerator you get cos squared plus sine squared, which is 1. In the denominator, you have cos squared, so you get the reciprocal of cos squared for the derivative of tan x, and that's usually written as sec squared x. The derivative of sec x is the derivative of 1 over cos x, and I'll use the quotient rule on that as well. So you have the denominator squared, and then for your new numerator, you have cos x derivative of 1, which is 0, minus 1 times the derivative of cos x. And when the dust clears, you've got sec x tan x. In the same way, we can show that the derivative of the cotangent is minus a cosecant squared, and the derivative of the cosecant is minus cosec cotan. With the added power of the chain rule, we can now differentiate complicated expressions involving trig functions. First example. The derivative of the sine of the polynomial 3x to the fourth plus 2x plus 5 is cosine of that polynomial times the derivative of that polynomial, which is 12x cubed plus 2. Now consider the point x equals 0, at which the derivative of this function is 2 times the cosine of 5, which is about 1.99, which is a modestly large positive number. This means that the tangent line has a modest positive slope, so the function is mildly increasing at this point. We get all this information from a simple computation without graphing the function. Second example, the derivative of 3 sine to the fourth of x plus 2 sine of x plus 5. Well, the derivative of a sum is the sum of the derivatives, so we just differentiate each term in turn. The first term, 3 sine to the fourth, tells us to differentiate the fourth power function first. Bring down the power, take the sine function to the next lower power, and you're done. Well, not quite. By the chain rule, you have to multiply by the derivative of what is inside the fourth power function. Inside that fourth power function was a sine function, and the derivative of sine is cosine. So you end up with 12 sine cubed cosine x. The next term is easy. You're just differentiating 2 sine x, and you get 2 cos x. And the last derivative is 0 because the derivative of a constant is 0. Third example, a composition of 2 transcendental functions. The derivative of the exponential of 3 cos x. Well, when you differentiate the exponential function, you just get it back. So you get e to the 3 cos x times the derivative of what's inside the exponential, which is 3 cos x. And that derivative is minus 3 times the sine of x. So the entire derivative is minus 3 sine x times e to the cos x. A fourth example, the derivative of 3 times the cosine of e to the x. In this case, you have a composite function with the trig function last and the exponential first. The 3 just factors out. The derivative of the cosine function is minus the sine of e to the x. And then you go inside that cosine function and differentiate e to the x, which just gives you e to the x again. Fifth example, the derivative of the tangent cubed of the polynomial 3x squared plus 4. Now this is a composition of 3 functions. The cubing function is the last function, the tangent function is the middle function, and the first function is the polynomial. So what you do is you differentiate the cubing function and you get 3 tan squared. And inside that tan squared, you don't change anything. You have 3x squared plus 4. You multiply this by the derivative of the function that's inside the cubing function, which is the tangent. The derivative of tangent is sec squared, and you don't change anything inside. You leave the polynomial 3x squared plus 4. So you get sec squared 3x squared plus 4. And then finally, you go inside the tangent function and differentiate 3x squared plus 4 to get 6x. As I hope you can see from these examples, memorization is not going to carry you through with complicated derivatives. You of course need to memorize the basic trig derivatives, but then you need a clear understanding of the chain rule. If you have mastered the chain rule, then something like the following is not at all intimidating. Ugly, yes, but not intimidating. The derivative of the cosine of the tangent of the secant of the log of x is minus sine of tan sec log x times sec squared of sec log x times sec log x tan log x times 1 over x. Now we turn to the inverse trig functions. Recall that the sine function is 1 to 1 when its domain is restricted to the closed interval minus pi over 2 pi over 2, and we usually label that restricted function capital S sine of x. The tangent function, in turn, is 1 to 1 when its domain is restricted to the open interval minus pi over 2 to pi over 2. And the restricted function is usually written capital T tan x. This gives us the inverse sine and cosine functions as sketched. There are two standard notations for the inverse functions. The inverse of sine is either written sine to the superscript minus 1 of x or arcsine x. And similarly, the inverse of the tangent function is written either tan superscript minus 1 of x or arctan x. I prefer the second notation in each case, which avoids confusion with the minus 1 power. The theorem for differentiating an inverse function is that the derivative of f inverse at a point y is the reciprocal of the derivative of the function at the point x, where y and x are connected by the fact that y is f of x. For the inverse sine function, this becomes the derivative of arcsine at the point y is 1 over the derivative of sine at the point x, which is just 1 over cos x, where y equals the sine of x, or equivalently, x equals arcsine y. So what we have is that the derivative of the arcsine function at the point y is 1 over the cosine of the arcsine of y. Now cos squared plus y squared is 1, so the cosine for y in this particular range can be written as the positive square root of 1 minus the sine squared of arcsine y. Well, if you take the sine of the arcsine of y and square it, you just get y squared. So the derivative of the arcsine of y is 1 over the square root of 1 over y squared. Replacing the symbol y by the symbol x, we can write the derivative of arcsine x is 1 over the square root of 1 minus x squared. If you find this argument a bit difficult, here's another proof. Write sine arcsine x, the composition of sine and arcsine applied to x, is identically equal to x, and differentiate this identity to get that the derivative of the composite sine preceded by arcsine x is identically 1. Now you can differentiate the sine, you get cosine of arcsine x times d arcsine x, using the chain rule, is identically 1. And the fact that sine squared theta plus cos squared theta equals 1 implies that cos squared of arcsine x plus sine squared of arcsine x is 1, which in turn implies that the cosine of arcsine x in this particular range is the positive square root of 1 minus sine squared arcsine x, which is just 1 minus x squared. So our formula for the derivative simplifies to cosine arcsine x times the derivative of arcsine x, identically 1, implies that, solving, the derivative of arcsine x is 1 over the cosine of arcsine x, which is 1 over the square root of 1 minus x squared. The derivative of the inverse tangent function is calculated using the same principles. The tangent of the arctan of x is identically x. Differentiate this, and you get sec squared of arctan x times the derivative of arctan x, using the chain rule, is identically the derivative of x, which is 1. Sec squared is 1 plus tan squared. So sec squared arctan x is 1 plus tan squared arctan x, and that's just 1 plus x squared. So our formula for the derivative of the inverse tangent function becomes derivative of arctan x is the reciprocal of sec squared arctan x, which is 1 over 1 plus x squared. It is surprising that our complicated friends, the inverse trig functions, should have simple rational and algebraic functions for their derivatives. Let's finish up with a few simple examples. Example 1. The derivative of the arc sine of e to the x. First you differentiate the arc sine, and you get 1 over the square root of 1 minus e to the x squared. And then you multiply that by the derivative of e to the x, which is just e to the x again. And then you simplify that to be e to the x over the square root of 1 minus e to the 2x, remembering that e to the x squared is just e to the x times e to the x, and that's just e to the 2x. The derivative of the arc sine of e to the 5x cubed. Well, more or less the same as before. Differentiating the arc sine gives you 1 over the square root of 1 minus e to the 5x cubed, quantity squared. And then you multiply by the derivative of e to the 5x cubed, and that is e to the 5x cubed times 15x squared. So when you clean it up, you get 15x squared e to the 5x cubed in your numerator, and in your denominator you get 1 minus e to the 10x cubed. The derivative of the arctan of the logarithm of 3x plus 1. Well, first you differentiate the arctan, and you get 1 over 1 plus the log of 3x plus 1 squared. Then you differentiate the log and get 1 over 3x plus 1, and then you differentiate 3x plus 1, and you get 3.